Greetings everyone, and welcome to Motion Map Examples. If you did your reading, you know that we are going to look at a different way of representing motion. It works okay in this unit of constant velocity, but it really gets useful when we start to talk about things that are speeding up and slowing down and things that are moving in multi-dimensions. So we're going to use this as a technique kind of all year long, and it will get more complex and more informative as we go. So to show you what a motion map is, I'm going to do two different examples. The first one is based on our toy car lab. Now all motion maps are consisting of three things. First of all, a position reference line. Now I know it's a position line because there's an X by it, and X stands for position, right? Horizontal position in this case. Then we're going to put dots above the position reference line. Those dots will represent the position of the toy car at equal intervals of time. And the dots are basically going to act like the blocks that we used in the toy car lab. Right? They're going to mark the position of the toy car every so many seconds, say. So the toy car started at a position 0. Position 0 is always over the tail of the arrow. That's the head of the arrow. Right? So that's the tail. So that's 0 seconds. 1 second later, the car had moved a little bit to the right. A few seconds after that, it had moved even further to the right. How much further? The exact same distance to the right. Why? Because it's moving at constant speed. And that means that it's moving at a constant rate, so same number of meters every second. So after 3 more seconds, it's here. After 3 more seconds, it's there. So notice these dots are all equidistant from one another because it's moving at a constant speed. Now, we are also going to put on a representation of the velocity. And now velocity, unlike speed, has two parts, right? It's a vector quantity, so it has a speed and it has a direction. So we need a symbol, something that we can draw that has a size and a direction. The perfect thing, arrows. And we're going to use arrows all year long whenever we talk about things that are vectors, because arrows have a size. Bigger arrows would be faster, smaller arrows slower, and arrows also point in a definite direction. So we're going to take a look at the velocity at each instant of time, meaning at each dot. So initially, as it crossed the 0 line, it was already moving because you started it behind, and it was moving to the right. So there's the velocity arrow at 0 time. 3 seconds later, it was moving with a constant velocity, and therefore the arrow should be the exact same size and point in the same direction. 3 seconds later, same velocity. 3 seconds later, same velocity. And 3 seconds later, same velocity, because after all, the whole point was a constant velocity motion. So you can see by looking at this motion map that it's a constant velocity motion in two ways. The velocity arrows are all the same length and point in the same direction, and the position dots are all equidistant. If we want to match it up with the motion, here we go. So you can see the toy car move constantly, and every so many seconds, the position dots, and then the velocity arrows. So let's look at a little more complex of a situation. Here we have a more complex motion. It's really 3 different constant velocities. And we're going to, in this case, I'm going to put a dot for each second. Now, we don't have to do that. We could put a dot for every 2 seconds or every 4 seconds. But I'm going to put a dot for every hash mark. Generally speaking, that's the way you do these. Okay? So let's start out at 0. At 0 seconds, notice that I haven't put numbers on the position axis. All right? But you can still tell that at 0 seconds, the graph is above 0. Now, in real life, that doesn't mean he starts out above the position reference line. Being above on a position time graph means that you start to the right of 0. So here's 0. Guy's going to start here to the right. 1 second later, he's further to the right. 1 second later, he's even further to the right. How much further? Well, since this is a straight line, it's a constant velocity, and therefore he's the same distance to the right. So here's the 0 second dot, the 1 second dot. The 1 second dot, and here is the 2 second dot. Now here's where we run into our first little issue. At 3 seconds, where is he? Well, he's at the exact same position he was after 2 seconds. So I can't just put a dot right on top of the other one, or you wouldn't be able to tell that a second had gone by. So what we do instead is we put it above. Okay? And this represents 1 second of stopping. Because remember, this is a position reference line, so you're at the same position. So again, this is 0 seconds, 1 second, 2 seconds, 3 seconds. After 4 seconds, he's still exactly in the same place. So we put another dot above. After 5 seconds, he's still in the same place. So we put another dot above. Notice 4 dots, but only 1, 2, 3 seconds of stopping. You kind of have to look in between the dots for the time interval. So there's 1, 2, 3 seconds of stopping. Okay, and this gets us all the way to 5 seconds. Now, after 6 seconds, he's moving back again to the left. Now, first of all, we're going to stay at this level. I don't want to drop back down because we'll start to overlap and that would get confusing. Okay? Again, the motion map is a representation of the motion. It's not the actual motion. We'll show you that with the little walking guy, but this is just a different way of representing it. So after 6 seconds, he's moved back, but notice he hasn't moved back as far as he moved forward in 1 second. This is less steep. Right? So he's not going to quite be back to this dot. After 7 seconds, he's again moving more to the left at the same velocity as he was here, so these two are equidistant. After 8 seconds, even more to the left. And notice here, after 9 seconds, he's now just past 0. Right? He's just to the left of 0. Look at 0. So if you've drawn this well, these should all be equidistant, and this dot should be just to the left of 0. Then after 10 seconds, he's even further to the left. So notice, fast velocity here, right, because big separation between the dots, not moving at all here because all these dots are at the same position, and then a negative, slower velocity because it's to the left and there's less distance. So now all we have to do is put the velocity arrows on. Initially, right, he's moving to the right and fast, moving to the right and fast. Notice these are big arrows. Then he's stopping. Well, if he's not moving, then that's 0 velocity, and therefore no arrow. So no arrow on the 2 second or 3 second or 4 second dot. But after 5 seconds, now he's moving again. But this time the slope is negative and less steep, so negative and slower. So he's going to move to the left and slower. Notice this arrow is smaller than these arrows. See, if you place the dots right, you can put arrows in between the dots and the size of them will work out correctly. Then constant velocity to the left. So all the arrows are the same size. Should there be an arrow on this last dot? Really doesn't matter to me. We really don't know what happens afterwards. We're mainly looking at these for the patterns and what they show about the motion. So again, you can see it's a fast positive velocity, then no velocity, then a slower negative velocity. And he ends up to the left of where he starts. So let's see what that motion would look like. And by the way, notice how many dots there are. There's 10 seconds, but there's 11 dots. And don't forget, you need to put the first dot means 0 seconds. So let's look at the motion. Our little guy is starting to the right of 0, and here he goes. Fast, stops, and goes back to the left slower, crosses 0, and ends up to the left of 0. So watch that one more time. It's a pretty complex motion. Moving to the right fast, stopping for 3 seconds, moving to the left slowly, crossing 0, and ending up to the left of where he started, right? And to the left of 0 for that matter. So here's 2 different representations of the motion, a position time graph and a motion map. And the motion map is probably a little closer to the actual motion. It takes a little less interpretation, but it's still not the motion. He doesn't go up here, right? He just stood still. So you still have to combine this with the actual motion. You have to interpret a position time graph, and you have to interpret a motion map.